Hello, my name is Cass, and I made a video game called Breakup, and it's available now on Steam Early Access. I'm making this video to fight some common misinformation in the game development community. As the title of this video says, I made this game without a game engine in just 2 months. I want to tell you how I did it, so you can feel empowered to do the same. My primary goal with this game was to produce something sellable in the minimum amount of time possible. This doesn't mean I wanted to half-ass it. I wanted to make an actually good video game. I just didn't want it to take a long time. When I'm looking for interesting, simple game ideas, I often turn to old video games, usually just playing random ROMs for systems from the 90s and seeing if anything grabs me. Even bad old video games can be great for this. They often have interesting ideas that the team simply couldn't deliver on with the available hardware, but that you could turn into something really compelling with modern technology. In this case, the game that caught my eye was a Super Nintendo game called Holy Striker, released in the US as Fire Striker. Holy Striker is an interesting little fusion of a Zelda-style action RPG with the Atari 2600 classic Breakout, or maybe a little bit of pinball. Immediately upon playing it, I recognized the potential of this idea, even as I recognized the game's flaws. Primarily, it feels kind of atrocious to play. The ball physics are too fast and floaty for my liking, and I think most of the enemies take too many hits to kill. The next phase for me was prototyping, where I threw together the simplest possible version of the game and made some adjustments. The main thing I did was step away from making a straight-up Holy Striker ripoff by instead restricting myself to traditional Breakout controls. My initial idea was to take cues from games like Hyper Light Drifter and create a movement system for the character that felt really satisfying, but I quickly realized both that I was not cut out for that from an implementation perspective, and that a huge amount of game feel is animation. And with the simplistic art style that I could pull off alone, I was not going to hit my aesthetic goals. During this prototyping phase, I suddenly had the idea, what if the ball just went off the top of the screen? What if it still had the little gravity that the ball in Holy Striker has, and the camera would pan up to track the ball? Prototyping this with some basic block generation, I quickly found it to be extremely fun, and I found my angle. It was with this design tweak that I decided on my guiding light, a roguelite from 2015 that I love called Downwell. I had set up from the beginning to turn this game into a roguelite because I want dollar bills. Sorry, no more complicated reason there. However, I have rather particular taste in roguelites. I'm definitely more of a Spelunky kind of gamer than a Hades gamer, if you catch my drift. I appreciate Downwell because it straddles the line between the austere, pristine approach of Spelunky and the dopamine-maxing, ultra-maximalist approach of Hades. Downwell features lots of little moments designed to please the lizard brain and unlockable characters and color palettes to sate the appetite for progress, but the gameplay itself was designed with an elegance and purity that I could really respect and enjoy. So with this vision in mind, let's talk at length about the more technical aspects of game development. I've been making video games since 2010. In that time, I've used a lot of different tools. RPG Maker, Love2D, Monogame, and most of all, Unity, which I used for just about every game I made from about 2014 to about 2019. I tell you this because I want you to know that while I'm about to say some mean things about some engines, this isn't coming from a place of ignorance or a place of malice. Every game shipped is a miracle, no matter what tools you use. If you like working with the tools you're working with, you don't have to change. But if you're often frustrated, I want you to know that making video games is hard, but it doesn't have to be this hard. Almost everything I have to say on the subject of making a custom engine has been said before me by Tyler Glale, who is most well known for working with Ed McMillan on games like The End is Nigh. The bottom line is that I don't think you should make a game engine, or that you should even think about what I did here as making a game engine. All I did was make a game, and I happened to do it without using any of the big engines. If you go into making a custom engine wanting to make something that replicates all the features of something like Unity or Unreal, you're going to fail. The good news is that, especially if you're making a 2D game, the feature set you need to make your game is likely a tiny fraction of what Unreal or Unity has, and you can easily implement it all in a month or two while working on your game. To quote Tyler, make a game at the same time as you're making the engine. This is an unbreakable rule, the only unbreakable rule. Get the basics in as fast as you possibly can, and then immediately start making a game on top of it. An engine is nothing without a game. As we get onto the technical details here, you'll hopefully see more and more of why what I wanted to do would have been substantially more annoying in a big engine than it was with my custom tech. The big reason I use a custom engine, however, is 3 words: Entity Component System. Specifically, the Moon Tools Entity Component System developed by my friend Evan Hemsley. Evan worked on Hyper Light Drifter and Wandersong, and it developed Moon Tools ECS and Moonworks in the process of working on a sequel to the 2013 game Samurai Gun. Now, if you're a Unity user, you might think, doesn't Unity have an ECS? You'd be right, but it's really bad. To explain why, I need to explain what ECS is and how it works. When people discuss ECS, they are generally discussing two different things and rarely specify which one it is that they're talking about. These two concepts agree that an ECS is made up of three things. First, you have entities, which are simple integer IDs that can have components associated with them. Components are simple collections of data that have no associated logic. In C#, I represent these using read-only record structs like this. All of the logic is put in the third type of thing, which is a system. Systems generally will iterate over every entity with a certain set of components using a filter, and perform some kind of logic based on the data within those components. For example, you might have two components, position and velocity. You might then have a motion system that filters for all entities with both components. It will then add the vector in the velocity component to the vector in the position component, and write that value back into the position component. Where the two ECS approaches differ is in how they store this information so it can be easily retrieved later. The most basic approach is what is usually called sparse storage. With sparse storage, each component gets stored in its own array. Whatever storage system you have then keeps a lookup table that lets you see which component belongs to which entity ID. The theoretical problem with this is that when you want to retrieve all the entities with multiple components, like we said above, you have to access random locations in separate arrays. This does not make the CPU happy and causes some cache misses. We can theoretically make better use of the CPU cache with the second approach, which is what DOTS uses and what just about every publicly available ECS library uses. This is commonly called archetype storage. With archetype storage, every entity with the same combination of components is stored in the same array, so filtering becomes just iterating over that one array. This makes the CPU very happy, and makes optimal use of the CPU cache. So what's the problem? The problem is that this approach completely breaks and performs horribly if you are frequently adding and removing components from entities. You can program a game in such a way as to avoid doing this as much as possible, but I find that it's absolutely horrible ergonomically. You wind up having to couple together a lot of unrelated data and totally lose the component mixing and matching that makes sparse ECS so powerful and fun to use. It also makes impossible the really useful pattern of using empty components as flags. It's not just me who thinks this. At the risk of coming across a little rude, there's a huge gap between how ECS is being used at real game studios and how it's being used by hobbyists who write libraries for fun without ever shipping games. To my knowledge, 2 AAA games have shipped in the past 10 years that use ECS as their main architectural pattern: Overwatch and Alan Wake 2. Both of them use sparse storage. I'll be ready to listen to the archetype storage people when they start shipping games. I've used Moontools ECS on 6 game projects spanning a huge range of genres since 2019, and I have yet to see a downside significant enough to make me want to ditch it. ECS is generally more performant than equivalent actor model code, but that's not really why we use it. Don't think of it as a magic bullet that will make your code run faster. If you're still worried about performance, know that every game I've built with these tools has easily blown past performance targets as long as I was keeping in mind how to make optimal use of the GPU in my renderer. If I built everything like Casey Muratori and Mike Acton told me to, I could maybe improve performance marginally, but once you're under 16 milliseconds a frame on laptops people pull out of ancient Egyptian tombs, there's really no point in optimizing further. Performance is extremely important, and you should think about it while you're programming because some optimizations are very hard to find by profiling after the fact, but don't be silly and waste your time optimizing code orders of magnitude beyond what you actually need. So Moonworks is the C# game framework developed by Evan Hemsley for the development of Samurai Gun 2. It's a C# wrapper around Evan's SDL GPU API, as well as the F-Audio audio library and the libdavid AV1 video player library. It also provides built-in SDF font rendering capabilities. We'll talk about that in a bit. SDL GPU solves a huge problem in game development right now, which is the fragmentation of graphics APIs. On Linux and the Switch, you have Vulkan. On Windows and Xbox, you have Direct3D 12. On macOS, you have Metal, and the PS5 has its own proprietary nonsense. SDL GPU and SDL Shader Cross, both of which are built in and easy to use in Moonworks, let you write API-agnostic code that runs on all platforms. You can write code in GLSL, HLSL, or MSL, and it will be automatically transpiled at launch to the shader format used by the platform the game is running on. You can get some of these benefits by just using SDL GPU directly in C, C++, Zig, Rust, whatever, but I think Moonworks provides enough of its own benefits to be worth using over just SDL GPU. This is going to be a shorter section because, honestly, Moontools ECS and Moonworks is itself a good enough reason to use C#. Another reason is that it's what I'm familiar with from years of Unity development, but this is a smaller reason than you might think. I've used a lot of programming languages over the years, and I have no trouble learning new ones. The real reason why I use C# and why Moontool's ECS is written in it is because it strikes a really good balance between usability and performance. It has a garbage collector, which you can rely on in some circumstances as long as you're not doing so every frame. Over the past several years, however, the C# team has been adding more and more systems programming-oriented features, such as the span collection that allows you to represent a contiguous region of memory with less overhead than the built-in array class. The performance of both the compiler and the runtime have been improving dramatically as well. Every major .NET version usually brings with it a 20 to 30% performance improvement completely for free. .NET also recently added the native AOT compiler option, which allows you to build C# code directly into native code you can run on video game consoles, totally eliminating the need for C# to C++ transpilers of days past. The toolchain I'll describe through this video works great on the Nintendo Switch, PS5, and Xbox. The worst thing about C# is definitely the build system, which is only marginally less baffling than CMake and pales in comparison to the modern build tools found in languages like Rust and Zig. So though, build system pain is generally a short bit at the beginning of a project, and then it just works for the rest of the development. It's not enough to make me want to ditch the language. One of the biggest benefits of writing your own renderer is the ability to build extremely simple rendering pipelines that only do what you need for your game. As an example of this, Breakup's engine does not have the ability to render sprites, at least not traditional sprites. This might sound crazy, but hear me out. There are two fundamental types of rendering, raster and vector. Sprites are raster graphics. Raster graphics are the kinds you're familiar with if you've ever used Photoshop or like MS Paint. You can think of them as an M by N grid of pixels. Sprites have a fixed resolution. If I wanted the game to look good on, say, a 4K monitor, I would have to draw that sprite at a resolution such that when displayed on a 4K monitor, there would be no aliasing. If I used a lower resolution sprite, when it was scaled up to the 4K monitor, you would be able to see artifacts along any curves and any lines not orthogonal to the pixel grid. Vector graphics are what you get if you use a tool like Adobe Illustrator. Instead of storing pixels, vector graphics represents an image out of simple geometric primitives like shapes, lines, and curves. These primitives are then rasterized by using math to determine which parts of the output image should be colored in. The cool thing about vector graphics is that they're resolution independent. I can run the rasterization math at any resolution I like, and I will get the maximum quality representation possible for that resolution. In a sense, GPUs are built to do vector graphics. The representation of a scene you send to the GPU is constructed out of triangles that are specified in world units entirely independent of the output resolution. However, they struggle when rendering curved shapes because the GPU can only think in terms of straight lines, so all curved surfaces have to be approximated. On top of that, this approach can still result in aliasing, like you can hopefully see here in this circle rendered from a 3D model. Normally I wouldn't care all that much about aliasing, but the aesthetic of this game was intended to be ultra crisp and vectorized, so I had to care or else it would look half-assed. The way the game is rendered now combines two techniques that sound scary, but actually aren't that bad. Compute shaders and signed distance fields. Signed distance fields were popularized in computer graphics for text rendering by a white paper from Valve's Chris Green at SIGGRAPH 2007. A signed distance field is a surface that uses a number to represent the distance each point is from the edge of a shape. The number is 0 at the shape edge, positive when inside the shape, and negative when outside the shape. Theoretically, the shape is continuous, but we can store discrete samples of this shape in an image, where each pixel is a sample of the field's value at a particular point. We can then sample this image in a shader and use linear interpolation to recover the approximate values of the input function. That was a lot of jargon. An analogy that might help clear up how this works is to compare it to digital sound. Digital sound works by sampling the amplitude of the incoming audio signal at a fixed sample rate. The original signal can then be reconstructed by drawing straight lines between the samples taken. The Nyquist-Shannon sampling theorem shows that the original signal can be reconstructed perfectly as long as your sample rate is twice the maximum frequency in the signal. This works out great for sound, because human ears can only hear up to 20,000 hertz, so if we use a sampling frequency of 40,000 hertz or more, we can reconstruct the input signal perfectly. Now, our example is a little different because our signal isn't formally band limited. However, the kinds of images we'll be working with mostly have low frequency information, i.e. they don't contain a ton of fine detail, so we can use a really low sampling rate defined by our SDF image resolution and still capture all of the detail of the input graphic. This is how SDF lets us use a really low resolution texture to draw a much higher resolution graphic without any loss in quality. Breakup uses a tool called MSDFgen to create signed distance field textures from SVG files. MSDFgen uses a much more advanced technique where it stores multiple signed distance fields in each of the different color channels of the texture, which allows for more accurate recreation of sharp corners, which are the kind of fine detail that a low-resolution SDF texture can easily miss. Okay, so we can render high-resolution output sprites with anti-aliasing from much smaller sprites generated from SVG files. How do we actually, draw sprites to the screen? The GPU can only process 3D graphics, so all sprites in most modern 2D games are actually quads, two triangles stuck together and positioned facing an orthographic camera to give the illusion of 2D rendering. We could just draw one quad for every sprite we want to render, but we can actually do better. We can batch all of these quads into a single draw call. This is faster in the same way that baking 2 dozen cookies at once is faster than baking them one at a time. You can construct this batch on the CPU, but that involves doing a lot of matrix math to determine the location of the vertices based on where you want the sprites to be drawn and how you want them scaled and rotated. That kind of matrix math is exactly what a GPU is designed for. Instead, we can use a compute shader to take all of our sprite data and turn it into a vertex buffer in parallel, and then use that as input into our SDF rendering shaders. There's more to it, obviously, but the whole file is only 600 or so lines, and the vast majority of that is setup and configuration. I wrote the entire thing in about 2 hours total, and I didn't have to give Fry a Homer $100 to render my SVGs. A wise man once told me that action games are just complex sets of rules for what happens when things hit each other. This means that collision detection and resolution are the beating heart of any action game, and it's exceptionally important to get them right. The first thing you must do when you decide to make an action game with a custom engine is realize the difference between collision and physics. Collision is enormously important, and virtually any video game that is not entirely menu-driven will require it. Physics is something you don't really need unless your game very specifically revolves around some kind of detailed physics simulation. You can get really high quality approximations of common, quote, physics behaviors with nothing but simple collision systems, and people did it for a really long time. The benefits of an entire rigid body simulation will simply be lost on the vast majority of game projects. There are two steps to video game collision: detection and resolution. Detection is determining that there's a collision at all. Resolution is deciding what to do about it. This means both preventing solid objects from overlapping, but also dealing damage, making the ball bounce, etc. The collision in Breakup is as simple as collision can possibly be. The basis is the axis-aligned bounding box. This is a rectangle with the added constraint that its sides are always aligned with the world axes. In other words, it can't rotate. This might sound extremely restrictive, but games have used axis-aligned bounding boxes for an extremely long time. For an example of where they're commonly used today, look no further than fighting games. Fighting game fans often look at images like this one, which show the areas of a character that can be hit to deal damage, and the areas of a character which can be hit for damage. Look at how comically oversimplified this is as a representation of the character's actual pose graphically. Nobody complains about this. Okay, well, they do, but only when the misalignment is so egregious that it feels misleading. Millions of people play these games around the world every day and never notice that the collision boxes don't perfectly line up with the graphics. Similarly, take a look at Breakup's colliders. Breakup is an even more ideal case than fighting games because the majority of its colliders are meant to represent graphical rectangles. Now, why would we use these bounding boxes? The reason is that their simplicity extends to their implementation. You can determine if two axis-aligned bounding boxes are overlapping with a series of 4 simple comparisons, as opposed to the more complex separating axis theorem and GJK algorithms necessary to determine collisions for arbitrary convex polygons. The core algorithm, then, is to try to move each object according to its velocity, check and see if the desired movement would result in a collision, and prevent it if it would. This covers the main parts of both collision detection and resolution for solid objects. To check if a movement would result in a collision, all we have to do is check the moving object against every other object in the scene that has a collider. Okay, hold on. That seems bad. And indeed, it is bad. The thing is, whether or not this is a problem extremely depends on your game. Hold on to your seats because we're about to do some math. If you've been programming for a while, you might have heard of something called Big O notation. I'm not going to get into the weeds here, but Big O is a way of representing the amount of time an algorithm takes. An algorithm with Big O1 runtime takes the same amount of time no matter the size of the input. An example of this might be getting an item out of an array when you know its index. An algorithm with Big O(n) takes more time the more inputs it has, but only linearly. An example of this might be finding a particular item in an unsorted list. If the worst case, this will require you to check every item in the list because the one you're looking for is the last item. In this case, n is the number of items in the list. Now you might think that the collision algorithm we described is big O n factorial because we have to check every combination of two colliders. However, in this case, order doesn't matter. Two colliders overlapping is the same no matter which one is first. So really it's n choose 2, which grows at a rate of big O n squared, which is much smaller than big O n factorial. In practice, it's even better than this, because we can perform a simple optimization by only checking moving objects against all the other colliders in the scene. A collider that isn't moving will only ever be involved in a collision with colliders that are moving, so this will still capture every collision in our scene. The real lesson here, though, is that what an algorithm's big O notation means for you is highly dependent on what n is going to be for practical cases in your use case. A key optimization for me was to have the in-game collectible particles not use the collision system. Instead, they're simply moved towards the player along a quadratic easing curve. This meant that in practice, I am only ever looking at two moving objects, the ball and the player. There can be multiple balls in play, but there will never be like hundreds or thousands of balls in play. If we assume two objects, then even with the bounds plus a full screen of 225 blocks, that's only 450 comparisons. 450 axis-aligned bounding box comparisons per frame is like, it's a lot to do by hand, but for a computer it's peanuts. And in practice, the number is always much less than that. There are lots of potential solutions to this problem for games that need it. This class of algorithms is called a collision broad phase. Available collision broad phase algorithms include KD trees, octrees, and the one that I usually use, a spatial hash. If you take nothing else away from this video, let it be this. I was able to ship Breakup without a collision broad phase just because I thought carefully about what my requirements actually are. When you start thinking like this, custom tech becomes extremely easy. Finally, we get to collision resolution. What I do for this is make use of a popular ECS feature called entity relations. These are essentially components that are attached to two entities instead of one. When two objects are colliding, I relate them with a colliding relation. Then, in my collision system, I filter for all entities that could be involved in a collision, i.e. every entity with a position in a bounding box. Collisions are then resolved via sequentially running methods like this. This is the simplest one, the functions that handles giving the player an extra life. It checks to see if the colliding entities have the appropriate components, and then performs the appropriate logic. A challenge you might not expect when you decide to write your own game engine is asset management. Put simply, how do you get all your little sounds and pictures into the computer program? Engines like Unity, Unreal, and Godot have huge amounts of code dedicated to solving this problem because they need to support a huge range of possible use cases. Breakup uses the simplest solution possible, an automated code generation script called content.py. I've used this approach on a number of projects now, and I'm really sold on it being the best way to manage assets for like a small to medium-sized project. I wrote the script in Python, but it could easily be whatever you're comfortable with. Ruby, C#, Bash script, whatever. You pass the script your asset source folder, and then where you want it to put the final assets, then your C# project file. First, it goes through all the assets that need processing to be turned from a form where it's convenient to work on them to a form where it's convenient to load them in the game. Shaders get compiled with GLSLC, the SDF textures get generated with MSDFgen, the sounds and music get transcoded with FFmpeg, and the font atlases get generated with MSDF atlasgen. The next step is the important part. One common approach to this problem is to have the game go through all the files at runtime and put references to the assets into something like a hash table. I instead do this at compile time and write code to auto-generate a huge C# file with all the data in it. Code generation often implies something really complicated, but here I'm just doing basic string manipulation in Python. The structure of the code is highly predictable and repetitive, so it's both an ideal candidate for automation and can be generated without the use of higher level data structures like an abstract syntax tree. This code isn't aware of the actual structure of the code at all, it's just writing strings to a file. Each texture atlas, for instance, gets its own auto-generated C# class, and each sprite is a field of the class. The benefits of this approach are that unlike with a hash map or other type of runtime lookup operation, which catches errors at compile time. If I change the name of an asset, it's a compile error, and VS Code will helpfully tell me everywhere I need to change the names of the assets. It's also technically faster than common approaches based on hash maps, although the performance difference is negligible. Everything else about making Breakup was basically the same as making a game in any popular game engine. When I stopped using Unity, the number one thing I learned was how little it was actually doing for me. Talking about custom tech often gets me and others labeled as elitists, but honestly I feel like I'm anything but. I believe that you're smart enough to make games without relying on tech from snake oil salesmen. You can make tools for yourself that fit your workflow precisely, and enable you to create faster than you ever thought possible. Thanks for watching. I plan on posting more videos like this in the future, so if you liked this, hit that subscribe button. Also, please buy my game. It's out now. Link in the description.